Hi everyone, I'm Himanshi, a PhD student at Monash University, and today I will be presenting a few recent results on the kinematics of spiral arms in the HD 142-527 system. To start off with a brief summary on the source, so HD 142-527 is an intermediate mass pre-main sequence star located approximately 150 parsecs away with a low stellar mass companion in close orbit. The second binary disk surrounding this pair consists of a gas pressure dust trap that gives the dust component of the disk a unique horseshoe-like morphology, which is seen in millimeter to sub-millimeter wavelength thermal continuum emission that primarily stems from dust grains. So looking at gas emission at millimeter wavelength, on the other hand, reveals several large-scale spiral arm structures that extend to distances of up to 650 AU from disk center. In a recent study by our team, we used ALMA observations at 0.3 arcsecond spatial resolution and found that the same spiral arms but traced at two different disk altitudes using 12 and 13 CO gas tracers were radially offset. So in protoplanetary disks, temperature is expected to increase from the midplane up to the surface layers. Due to the varying optical depths between 12 and 13 CO isotopologues, emission from 12 CO is tracing gas much higher up in the hotter disk layers than 13 CO, which is found further down and closer to the cooler midplane. So being gas density waves, the spirals propagate at sound speed, where the sound speed is dependent on the local temperature of the medium the wave is propagating through. Therefore, the presence of a non-zero vertical temperature gradient implied that the speed at which the spirals were propagating outwards varied between the two traces. So we made the conclusion that the radial offset we were seeing was due to the spiral arms surfing on this vertical temperature gradient, whereby the 12 CO spirals had propagated out faster and thus further, whilst the 13 CO counterpart spirals were trailing behind. Furthermore, these spirals were also found to not be in Keplerian rotation. When viewed through channel maps, the spirals are seen to extend into regions of the map that corresponds to either higher or lower velocities than the expected Keplerian velocity, thus deviating away from the bounds of expected Keplerian rotation. Focusing on the innermost spirals in particular, at extremely high blue shifted velocities, emission is seen to extend into a region of the map that would normally be occupied by emission at lower blue shifted velocities. This therefore makes the spiral super Keplerian in this region of the map. Conversely, this switches over in the redshifted region of the map, where the same spiral transitions to be sub-Keplerian. The perceived velocities here are likely a combination of both azimuthal and vertical motion in the disk, where a vertically ascending spiral would replicate the transition from super to sub-Keplerian rotation, because the Doppler shift in the red-shifted regions would be attenuated, whereas in the blue-shifted regions, the Doppler shift would increase. Thank you for listening, and for full details, please refer to our paper cited below. Thank you.